Hey, good afternoon, everyone. Welcome back to the Heidelberg Joint Colloquium. After we didn't have one last week, I hope everybody's GEMS web proposals went well and you've recovered from the email avalanche that followed. It is a real honor and pleasure to welcome Andrea Mignone today. Andrea did his PhD at the University of Chicago, which he received in 2004 after working with Robert Rosner. And after that, he took up postdoctoral fellowships at Torino Observatory and the physics department at the University of Torino. And in 2008, he became a permanent researcher there. And since 2016, he is an associate professor. And Andrea is a world-leading expert in the areas of astrophysical fluid dynamics, plasma modeling, high-energy astrophysics, accretion, and feedback processes. And he is maybe best known as the developer of the Pluto hydrodynamics code, which has 600 downloads per year and has now reached of the order 800 citations. And today he is going to tell us about frontiers in computational plasma astrophysics, connecting small and large scales. And as is the tradition at the Heidelberg Joint Colloquium, I would kindly ask everybody to unmute and welcome our speaker today with a very warm applause.
Well, thank you, Diederik, for the nice introduction. So I assume I can start. So today's talk is going to be on frontiers in computational plasma astrophysics, and I would like to talk very much on the connection between small and large scales. So this is a list of close collaborators that has contributed to the result that I'm going to show. But let's start from the outline. Since the talk is quite long, I have divided in a number of subsections. So I will introduce first astrophysical plasmas and start from observational evidence with a special eye on high energy astrophysics and high energy astrophysical environments. Then I will talk a little bit on theoretical and computational modeling of such objects. And discuss the application to AGN jet propagation. So what we know so far from the large scale. In the following parts, I will discuss how the scale connection can be developed both on the numerical side and the theoretical side. So we'll talk about adaptive mesh refinement on one side, and then I will introduce hybrid models that use at the same time particles and fluid, okay? And then the summary at the end. But first, astrophysical plasmas. Let's see the observational evidence. So maybe it's obvious to you, but it's important to start from the fact that we estimate that 99% of the visible matter in the universe exists in the form of a plasma, which is essentially an ionized gas where particles are charged and can feel each other through long distance forces. There are several examples that you know: stars, nebulae, galaxies, supernovae, jets, accretion disk, and so on. Now, the second important point to remember is that whatever we know about this object can only come from the radiation that we can see. So we are dealing with the emitting plasmas. Now, if we focus to a particular high energy class of these objects, then I would like to talk about jets from active galactic nuclei, which are collimated outflow produced in the central region of radio-loud galaxies. Okay, so they are powered by a supermassive black holes, and they can extend from, well, the inner region, which is a parsec scale, up to the kiloparsec and then megaparsec. So we are talking about huge objects here. Now, the spectral signature characterizing these objects is typically non-thermal, okay? And the radiation comes essentially from synchrotron and inverse Compton mechanism in the X-ray and the gamma bands. There is a huge kinetic power ranging from 10 to the 42 to 10 to the 47 ergs per second. The lifetime is about a few millions here. And some of these objects, especially blazars, are characterized by a strong variability that can happen or can take place on a few days. Now, morphologically, these objects are classified into low power sources or high power sources, depending on whether the emission comes from close to the central region, like we see here in 3C31, or far away in the hotspot, like 3C98. But it is believed that they should be powered by the same central engine. Now, there is a convincing evidence that we are dealing with supersonic relativistic flows that are propagating in a partially ordered magnetic field. However, after many years of investigation, it's still not clear how to constrain the parameters such as the jet velocity, density composition, magnetic field topology, and strength, okay? There are several questions concerning these objects, and numerical simulation have helped us in the last decades to answer partially at least some of these questions. So for example, what affects the morphology? I mean, why these jets are bending and we see them deflecting away from the main propagation axis? And this is believed to be caused by fluid instabilities, and I will talk about this in a little bit. And the second most important question is how is the jet able to dissipate the energy and make the kinetic energy available to accelerate particles, okay? So this is not completely clear, but it is probably due to also instabilities and the possibility to convert kinetic energy into thermal and then accelerating particles energy, okay? Now, if you look at the typical spectral energy distribution of these objects, it is mainly made of two peaks, two broad humps, okay? One is it's a low energy peak mainly in the millimeter UV band, which is due to synchrotron emission. And then we have a high energy peak in the X and gamma rays band, which is thought to be caused by inverse Compton scattering. Now, as I mentioned already, blazars exhibit a short time scale, which is less than a day. And that means that there are very compact regions where a sizable fraction of the jet energy flux must be dissipated. Now, how this is actually achieved is not totally clear. But the point is that if we dissipate energy, then we can make this energy available to accelerate particles. And you know, a particle that is being accelerated can emit. So this is a crucial step in understanding how the emission process is originated. There is another class of objects different from AGN, which is a galactic origin, which are pulsar wind nebulae, but they share many similarities. Now, the pulsar wind nebulae are powered by the spin down of young neutron stars that are losing energy in the form of a relativistic magnetized wind. There is the wind composition is probably made of pairs, and also a small amount of hadrons. And the fact about pulsar wind nebulae is that they are very interesting objects since they can achieve relativistic energy, but they have galactic origins. So we have more information available. So they are, in a sense, a little bit easier to study, okay? It's because the comparison with observation can be done more accurately. Now, let's talk about dissipation. Now, if we zoom, dissipation occurs on a small scale. Okay, it's not a large scale process, it's a small scale process. And you can, from theory, you can actually find three main acceleration sites, dissipation sites. One is collisionless relativistic shocks, which are able to dissipate kinetic energy into heat very efficiently. Now, these are prominent sites to accelerate particles through Fermi first order process, okay? However, their efficiency may be limited to strongly magnetized case and also to those shocks where the magnetic field is aligned with the propagation of the shock. A second mechanism, which is probably even more promising for producing high energy particles, is relativistic magnetic reconnection. And there is a lot of work going on, especially in the last 10 years after the introductory work of Sironi and Spikoski in 2009. Third, and also quite important, but not so well explored, is the velocity shear. I mean, particle can gain energy by scattering off small-scale magnetic field irregularities within a turbulent velocity shear layer caused by, for example, the generation of Kelvin-Helmholtz instability modes. But now I will first talk about the large scales, and then I will slowly move down to the small scales, okay? So what can we say about the connection between the two scales? these processes cannot be studied simultaneously on both scales. I mean, you have to choose. Either you focus on the small scale and therefore meaning small temporal scale and spatial scale, or you either go to large scales, meaning I focus on very large scale and very large time, okay? Therefore, our computational modeling is very fragmented under the limited approaches. On one side, on the small scale, you have a kinetic theory helping you together with PIC particle in cell codes, okay? But if you move down to the large scale here, then you have MHD, which is a fluid theory. The two approaches are separated by many, many orders of magnitude, and there is no way you can make a numerical simulation that can cope with both scales. Kinetic will be too demanding to extend to high scale, and fluid will be too demanding to include also kinetic effect. So there is a huge scale separation. Now, the kinetic descriptions, as I said, is done by PIC particle in cell codes, which are very good codes to study plasma physics. However, they are applicable to study small regions of the size of a few thousand kilometers on a temporal range that it is the order of a few hundred seconds. However, there are you can then move down in this graph, down, so from PIC to hybrid and then to fluid. First, you encounter hybrid kinetic models, essentially, where you build, you model the electrons as a fluid and the ions as particles, okay? So they must resolve the ion inertial length, but then you can move down to 1 astronomical unit and extending the time range to a few hours. If you still move down, then you approach the complete fluid model with MHD, where only magnetic and light waves must be resolved. And at that point, you can afford to model very large system scales. So you can start from a classical description, all right, which is essentially, I try to build the plasma equation from very scratch, okay? So I model each particle. So I have individual particle of motion, then I have the link between charge and current given by the second box, and then finally Maxwell's equations. However, as you can easily realize, this is not feasible because you have way too many degrees of freedom. So it's basically impossible to model every single particle in your system, okay? So no computer is able to do that. And even if you could do it, you would have too much information to process out. So you can sacrifice the classical description in favor of the kinetic description, where instead you start from the kinetic equations, such as Vlasov equation, which is the evolutionary equation for the distribution function for a given species, okay, given the number density per unit element of phase space. Particle in cell code are essentially a finite element approach to the kinetic description, okay? Essentially, they describe particles that are given by the superposition of several elements, superparticles. So in other words, each element can be thought to be a large number of physical particles that are near other in phase space. Now, this is a very consistent and very good approach, but in order to make a PIC code work, you need to resolve the plasma skin depth, okay, which is of the order of a few 100,000 centimeters. Sorry, my PowerPoint stuck. Okay. Then you can actually sacrifice the kinetic approach in favor of a fluid approach, where you treat the system as a continuous medium and you consider a small volume of the fluid. Notice that the small volume should be large enough to contain a significant, well, actually a statistically relevant number of particles, but at the same time to be small enough so that any macroscopic variation can be neglected across it. Now, the fluid equations are derived from the kinetic equation. So there is a connection between the two. But the point is that in order to do this derivation, you must take moments of the kinetic equation. In the end, you will end up with the set of equations for which the knowledge of the distribution function is not needed anymore. However, there is a problem here because each time you take a moment of this equation, you end up having an equation with a next higher order moment. So you need some form of closure in order to end up with a solvable system of equation. Sorry, I think okay, I was skipping this slide. So the way to achieve this is very simple. By taking the average in velocity space, then you build up macroscopic quantities such as density, fluid velocity, or energy, or whatever you want to do. The key process is that by doing this average, you remove all the information on the velocity. So all kinetical effects are neglected in this point because your distribution function could be very peaked, in which case it's okay, or can be very broad, in which case it's not so okay, because you are averaged down everything in velocity space. If you do this process, then the first set of equations you obtain is the two fluid set of equation, because you are averaging the Blasov equation for the electrons and then the Blasov equation for the protons, and then you have two set of equations, so continuity, momentum, energy, still coupled to the Maxwell's equation. So now we are full in the fluid description. It is valid as long as the size of the system is much larger than the mean free path. And now you are required to solve the nonlinear hyperbolic or parabolic partial differential equations. The two equations, system of equations, are obviously coupled by this term, which you see REI. Okay, we simply are the coupling term between the two species due to either collision, well, not through collision, but let's say Blasov-like collision, long distance. Okay, and you will soon realize, however, that this system also have some problems, numerically speaking, because since you are dealing two particles with different masses, protons and electrons, the time scale for the electrons will be much faster than the one for the protons. So then you are led to take very small time step for the protons, okay, in order to match the two equations. So the fact that we are dealing with particles with very different masses is a big problem in this in plasma physics. Then you can make a choice. You can say, well, let's average down the two sets of equations. So instead of considering two sets, let's merge them down, for example, by considering the fluid velocity, which expresses essentially the velocity of the barycenter of the two species, which will coincide, of course, with the barycenter, with the fluid of the protons, since they are heavier. Then you have a set of 15 equations in 21 unknowns, which are reported here. And still you need to adopt some closure to express the pi. So this big pi is the pressure tensor, while Q represents the heat transfer term. Okay. And then you are down here. So as you can see, through the derivation, we have moved down from top to bottom, so from small to large scales. Finally, then you approach MHD, because in MHD, you make a lot of simplified assumption by essentially assuming that we are dealing with a very low frequency plasma, that we neglect collision, we neglect electron effects, we neglect Larmor radii, and consider very large scales. And also that we are dealing with the fluid where the hydrodynamic processes and the electromagnetic processes will fluctuate on about the same temporal and length scale. This is MHD. So you also neglect charge separation, electric force, and displacement current. So after all, to be honest with you, MHD is really the most simple form of plasma description. This is MHD. So essentially, you can recognize easily the equation of hydrodynamics augmented by the Lorentz force on the right-hand side in the momentum, in the equation of motion, and Faraday's law, which is still kept to describe the evolution of the magnetic field. Now, as you see, Ampere's law is simply J equal to the curl of B. Then you can adopt a Ohm law, which tells you that the electric field is 0 in MHD in the rest frame of the fluid, because E is given by U cross B. So whatever electric field you see is only induced by the fluid motion. Then you have the divergence-free constraint and the closure, which gives expresses the internal energy of the fluid as a function of the density and the pressure. We are actually more familiar probably with this formulation, which is the conservative equivalent to the equation I just saw before. So it's called conservative because the equations can be written in divergence form, therefore stressing out the importance of conserving mass, momentum, energy, and etc. Now, MHD is suitable for describing the plasma at very large scale. I would say that it is still a good approximation to much of the physics, even if you don't meet some of the conditions. And it allows you to draw some intuitive conclusion concerning the plasma behavior without solving the whole system of the equation in detail. They are an hyperbolic system of conservation law. At the numerical level, most modern code will treat this system using finite volume approach. Which means essentially that you start from the differential equation, and upon integrating in space, you obtain an exact relation, okay, between the average value of a given quantity, such as density, momentum, or energy, through its net flux through the region boundary. In order to evaluate the flux term in square brackets on the right-hand side, you need to solve a Riemann problem, which is essentially the what happens to the decay of a discontinuity at a given interface. Essentially, in the fluid code, we have several zones. At each interface between one zone and the next, you have a discontinuity. The discontinuity will break down into a set of waves. These waves must be resolved, and your ability to resolve this structure will allow you to compute the flux. And then you can evolve the equation. So that's, in essence, finite volume formulation. And let me just introduce the Pluto code very, very quickly through one slide. So Pluto is based on a finite volume formulation. It solved the plasma equation in the context dedicated to astrophysical environments. So the target are multidimensional compressible high Mach number flows. Okay, it's freely distributed, and the version 4.4 just came out last week. Okay, let me now move to the application to relativistic jets. So what can we learn from numerical simulation? So what have we learned, and what are we learning, and what we will learn? So first of all, let me remind you that AGN are extending on a humongous spatial range, okay? Because the inner region are about less than 100 parsec. But then they are very much collimated, and they will extend and propagate up to the megaparsec scale. Now, simulations are not usually done by considering the whole process, simply because it's just too big. So you either consider the launching region, so the very small part around the black hole in the accretion disk, or you consider just the jet propagation by injecting the jet at some given distance from the central object. So it's either one or the other. It's very difficult or very challenging to model the system as a whole. Now, for example, in the context of FR1 and FR2, our group has carried some numerical simulations showing how the jet braking can be achieved in this source. The interesting fact is that jet braking can be achieved if you consider the propagation of a jet in a stratified medium whose temperature is increasing with the distance from the central source. Now, instead of having a normal jet, in this case, the jet energy, instead of being let's say, instead of having a terminal shock, you dissipate the energy gradually due to turbulence, and the jet spreads out smoothly while decelerating. This deceleration process gives rise to entrainment and mixing with the ambient medium, giving the characteristic plume-like feature of FR1 objects. I would like to stress that this simulation should be done always in 3D, okay? 3D is essential here. Just because the properties of turbulence in 3D are very much different from the properties of turbulence in 2D, okay? Because actually there is no energy cascade to small scales in 2D. Now, if you observe, if you do some cut through the meridional plane of the simulation, you will see that there is no evidence for the Mach disk. Those of you that are dealing with jets should know probably what the Mach disk is. Essentially the last part where the kinetic energy of the flow is converted into heat at the very end. So here is there is no evidence, just because the flow is a transition from a supersonic regime to subsonic. And this is due to the fact that the sound speed is increasing with distance as you move away from the source. So the jet is still collimated for about 30, 40 jet radii, and then it's become gradually dissipated outwards. However, if we now consider the strongly magnetized case, then the situation gets much more complicated for a number of reasons. First of all, strongly magnetized jets are described in terms of at least 5 parameters. Well, you have a sonic flow Mach number, exactly as before, and the bulk Lorentz factor. But that, and the jet ambient density contrast, which essentially tells you the ratio between the jet density and the ambient. This parameter is estimated to be less than 1 from a variety of studies carried out in the last 40 years. But then you also have the magnetization now and the magnetic pitch. The magnetization is usually labeled with sigma, and it gives you the strength of the field with respect to the bulk kinetic energy of the flow, while the magnetic pitch gives you the ratio between the poloidal component, BZ, and the azimuthal component, jet, okay? Because of course, the magnetic field can have a different topology. You can have field in straight lines or circles or open lines or whatever. So the topology of the field is actually very important in this situation, because as we shall see, that can lead to different morphology. If you indeed consider, for example, 2 different topologies, okay? One on the left side, which is mainly aligned with the jet axis, and one on the right-hand side, where the jet, or the azimuthal field is only azimuthal, so it comes in rings around the jet. Now, in the first case, where the field is poloidal, then you have straight propagation and non-significant deflection. But if you now use the same field strength by building a toroidal field, then the jet will start bending and deflecting, especially at the head of the jet. So the morphology is very much different in this case. So this is just to say that the topology of the magnetic field affects the jet propagation very much, causing therefore deviation from axis symmetry. We have also repeated this set of simulation by considering the jet from the Crab Nebula. Now, from this object, we know that the jet exhibits some variability, as you can see in the X-ray images taken by Chandra in 2001 and 2010, showed here, where you can clearly see that the jet has changed its morphology. So there is an S-shape here, which is not present in the same picture taken in 2001. Now, here also, we are injecting a jet which is partially toroidal and partially azimuthal, but it's more azimuthal. So it's a small pitch. Now, in this case, the jet is also being deflected from the main axis, showing this sequence of knots, which are essentially pinch mode, because there the magnetic field is compressing, therefore forming collimation shocks, and then which are expanding again, then being compressed again, and so on, to end up in the Mach disk, which is being dissipated while also being deflected. So these results are given for a Lorentz factor of 2 and a fairly modest magnetization of 1. If you now try to compare the 3D with the 2D, you will find absolutely completely different results, of course, but it should be obvious by now, because in 3D, the rise of these current-driven modes can only be seen in 3D because you have the M1 mode. So the M1 mode is the azimuthal mode. If you take a 2D simulation, that mode will be completely quenched, and then you cannot see it. Now, for the Crab Nebula, what we see is a deflection time scale is very much compatible with observation. So we believe that current-driven instabilities can be a very likely candidate to explain the change in morphology in these objects. Of course, there are many instabilities operating in these jets, not just current-driven, but a mixture of them. Very broadly speaking, we can actually recognize three sets of instabilities. The Kelvin-Helmholtz instability, which is driven by the relative velocity shear and that leading to mixing, momentum, and energy transfer and entrainment, and possibly to the jet disruption. But that depends very much on the configuration you are studying. The current-driven instability, or CDI, is driven by the parallel component of the current. It exists mainly in those situations where the electric current is aligned with the magnetic field. Now, in this case, you can have a small pitch and helical deformation of the jet, and you can see this is a typical M1 mode seen here. Then you have pressure-driven, which on the contrary are driven by the perpendicular component of the current. And they are very much more similar to interchange instability, such as the Rayleigh-Taylor instability, forming therefore small-scale structure. Now, in a jet, all three instabilities can coexist or mix up. So it's not always very easy to understand which is the main mechanism operating here, okay? But we believe that the pressure-driven are very much quenched by the velocity of the jet, while the current-driven and the Kelvin-Helmholtz actually mix up, okay? And this has been done in a number of papers published a few years ago by our group as well, and by other groups also. Okay, now that we have done a panoramic view of what can be done at large scale, let's move down to small scale, okay? Adaptive mesh refinement is a technique that allows you to concentrate the resolution on a given specific portion of your domain. Now, the details of AMR are quite complex, so I prefer not to talk about the technical details here, but just to tell you that with a good library and a good software, you can achieve actually resolution control over those portions of the domain that you are actually interested in zooming out. Just to make you an example, if you would like to study the interaction between a shock and a small cloud, then we need to enhance the resolution only close to the small cloud without having to resolve the full domain. And this will give you a considerable gain in terms of computational time, memory, and data and disk management also, okay? So adaptive mesh refinement it's a very useful technique. However, from my experience, I would say it works mainly when the region you are trying to resolve are occupy less than 1% of the computational domain. So the filling factor of the region you are trying to resolve must be very, very small. Otherwise, the computational overhead introduced by the AMR approach will end up making the simulation very heavy. Okay, but that's definitely a way to go, especially if you try to build in the future a hybrid model, or if you want to focus on a particular region of your computational domain. This is an example of what kind of speed up we can achieve with adaptive mesh refinement. This is a simple gem reconnection problem. So we are increasing resolution down here where the reconnecting current sheet, where the reconnection is taking place. So the static grid employs a 2048 times 1024, but with AMR, we can afford a much lower resolution with 64 by 32 zones, but using either 3 or 5 levels of refinement, ending up having the same equivalent resolution. Now, the speed up is given here in terms of parallel strong scaling. Now, with adaptive mesh refinement, you can actually be about 5 to 6 times faster with respect to the static grid computation. But for this particular problem, don't take this as a general rule, okay? It depends very much on how you refine and what kind of criterion. Of course, you will end up here by saturating the speed up curve for a very simple reason. At that point, the number of blocks that you create per each processor equals the total number of processor. At that point, you cannot scale very well because, for example, in our case, the strategy is that a parallel workload is done in such a way that each grid is separately distributed. So each processor can own only just one or more grid, but not half size of the grid. Okay. So there are also limitations from the parallel point of view, but these are more technical detail. I'll be happy to answer later on if you have questions on this topic. Okay, then let me talk a little bit about the connection between small and large scale. So this is a very important, probably the most important part of the talk. I hope you can still follow me. There are two models I would like to talk about. One is the MHD-PIC model for intermediate size, and then Lagrangian particle for large scales. Now, in order to move beyond standard MHD, we need more physics, okay? Because MHD is not sufficient to model a number of issues. Emission can not be addressed, for example, because we are completely neglecting kinetic effects. So we need to restore somehow, in some way, this kinetic effect into the code. There are different ways of doing this. One way that we are currently exploring and seems to be quite successful is to use particles to restore subgrid modeling or microscale physics. Now, the idea is that together with the fluid equation, which you see here, okay, the U over the T plus the divergence of T equal to S, you also have particle equation, and the two components are coupled by this acceleration term and the source term, broadly speaking. So fluid on one side, particles on the other. That's why we are talking about hybrid models now. One such model is the MHD-PIC model. The cosmic ray particles can be treated then using conventional particle in cell technique, while the rest of the plasma, the thermal part, is still treated as a fluid. Now, the advantage of the MHD-PIC approach is that it can properly describe the physics of the composite scheme on a scale which are, on scales that are much larger than the ion inertial length. So you can actually have a time step which is larger than the one that an equivalent PIC simulation will give you. So roughly speaking, we can say that if the PIC code are here, the plasma operates at the plasma skin depth and the MHD operates at the system scale, then the MHD-PIC is somewhere in between at the gyro radius system scale, as long as you can take the gyro radius larger than the plasma skin depth scale. Now, if you want to see the details of the equations, then here you are. Now on the left in blue, on the blue box, we have the standard MHD fluid equation, which are comprised of the usual one, so momentum, energy, continuity, Faraday's law, and energy. But you can see that there are some new terms, this FCR, which is essentially the Lorentz force acting on the particle. So the composite system for Newton's third law, you must conserve momentum. So if we act on the particle with the V cross B term, then the opposite of this force should be carried out on the fluid, okay, in order to conserve momentum by Newton's third law. And this is exactly what FCR is. So FCR is the macroscopic manifestation of the Lorentz force acting on the single particle. But there is another modification. Now, the cosmic ray, while moving, create a current. This current will actually enter in the Ohm's law. So your Ohm's law now will be slightly different. Besides the usual V cross B term, due to the fluid motion, you now have a term which is proportional to the relative velocity between the two species, gas, Vg, and cosmic ray, VCR. Now, one successful application of the MHD-PIC model is, for example, modeling the diffusive shock acceleration, which is the process by which we accelerate particle at shocks. So it is very well known that particle can actually be trapped across a shock and then becoming reflected from magnetic field or clumps in general, going then back and forth the shock and then gaining energy at each crossing. Now, this simulation that I'm going to show you now is an example of such a computation. So now we have a supersonic flow hitting a wall on the left, and then a shock is forming. Now, particles are injected at the shock position and they drive supersonically into the upstream, generating an instability, which is known as the non-resonant Bell instabilities. This instability will give rise to turbulence, which will feed back on the shock by corrugating the shock. At this point, particles are injected in an isotropic way, and they can actually cross the front, and by being reflected, they gain energy. Now, what you see here is density in the top panel, magnetic field in the middle panel, and the energy spectrum in the lower panel. Now, the spectrum broadens in time, okay? And it will eventually form a power law with the cutoff, which is approximately exponential here. Now, the dashed line here gives the theoretical prediction from first order Fermi acceleration, while the spectrum here is the computed one. So in order to achieve this simulation, you need to use millions of particles to do such an effect, okay? Because just some of them are becoming accelerated, because you also build up a tail at lower energies. Now, of course, I didn't show particles because there are way too many, but I made this movie for you. In this movie, I selected one of the most energetic particles in this configuration, okay? And the color of the particle here is indicating its energy. So red is not so energetic, white is very energetic. Now you will see that as the particle moves back and forth across the shock, it will change color, meaning that it's gaining energy. Don't worry, it's coming back, okay? Now, the particle motion here is comprised of standard gyration plus several drift, okay, which is the E cross B drift, gradient drift, curvature drift, and so on. Now, the irregularities across which the particle is reflected are magnetic clamps formed by the turbulence. Okay, the particle suffers multiple head-on collision across the shock and end up, as you can see, the particle has now turned white, meaning that we have a much more energetic particle. So this is really modeling microphysics. The process takes place after several thousand gyrations. This is important to remember. Okay, you can also apply the MHD-PIC model to more complex environments such as reconnection, for example. So for those of you who don't know what reconnection is, it's simply the topological rearrangement of magnetic field lines which are initially opposite directed. So initially you have in the upper panel, the magnetic field is pointing toward the right for me, left for you probably, and the opposite direction in the second half of the plot. Now particles are being, as you can see, as we will see later, they are being accelerated through the central midplane and become trapped in these features, big blobs, which are called islands, magnetic islands. Also here, the spectrum that you build depends on the magnetization, and it has a power law shape. Now, again, let me show you what happens to the particle. I just chose some particles here, not all of them. As you can see, there is an E cross B drift, which is conveying all the particles toward the central layer. But once the particle reaches the central layer, they experience a very strong magnetic field. This strong a very strong electric field, because we are reconnecting, so there is a high resistivity in that portion. In that region, the electric field can also not be perpendicular to the magnetic field. This is where the acceleration takes place. Afterwards, the particles become trapped inside the island, where they keep being accelerated at a slower rate. Okay, typically because now we have Fermi kind reflection, the particle is bouncing back and forth towards the walls of the island. So this is done only by using, there is no feedback in this simulation, it's pure test particles. Okay, let me now move to the second model I wish to talk about, the second and last model, because I think I have just 5 minutes left. Lagrangian particle. Now, modeling shocks and reconnection is nice as long as you are able to resolve them. But if you go to very large scales, then you won't be able to resolve such small, tiny features. In that case, you have to forget to possibly use a single particle motion. Instead, what you do, you consider the macro particle, which is an ensemble of real particles, for example, electrons, that are very close in physical space, but not so close in momentum space. In other words, each particle, which is represented by a dot in this figure, is an ensemble of many electrons having a spectral distribution. What you do now is that at those scale, you can safely assume that these particles are transported passively with the flow. However, each macroparticle has its own spectrum, and this spectrum changes in time according to a Fokker-Planck-like equation, which I reported here. Now, there are many terms here, which I would like to talk to you about. So one term is accounting for adiabatic expansion. Then the second term is accounting for synchrotron or inverse Compton emission. Then we go for shear acceleration, Fermi second order, and non-inertial term. Now, if you neglect a bunch of these terms, but you keep actually synchrotron adiabatic expansion, then you end up with an equation, which is the orange box equation, that tells you the distribution, essentially the temporal evolution of the distribution function of that particular macroparticle. And if you have millions of macroparticles, then you will resolve millions distribution function in that case. Fortunately, this equation can be solved analytically using the method of characteristics. Now, in other words, now if you try to model shock acceleration at this scale, this is what you end up seeing. The particle is standing still, and once the shock hits the particle, the spectrum will change instantly. Okay, let's see the movie again. Okay, and then you have synchrotron losses, and the spectrum will decrease in time. But the point is that at this scale, I mean, we're talking about several order of magnitudes above what we saw before, the process takes place instantaneously, essentially. Okay, so we know from theory how the spectrum changes in time. So we can apply essentially diffusive shock acceleration theory in order to predict the power law that will come out from this shock encounter. And then synchrotron emission will do the rest. Now, here is an example of a three-dimensional relativistic MHD simulation with the power between 10 to the 45 and 10 to the 46, a pretty large Lorentz factor, opening angle of 5 degrees. Now, in this simulation, you will see density in both plots. However, the plot on the left tells you the aging of the particle. That is the time that has passed since the particle has encountered a shock. Because in this model, particles can be energized only through shock encountering. On the right, you have the maximum energy of the single particle. And of course, the energy is being boosted each time the macroparticle encounters a shock. Okay, in which case, is for each of them, we adopt what I just showed you before. We reset the power law, and then we let the synchrotron emission do the rest. By doing this, so you are essentially putting recipes as subgrid models in your simulation. And as long as you can trust this recipe, then you are able also to predict the amount of photons escaping from that region by simply estimate how much energy I'm losing because of a particular process. So I can compute the surface brightness of the jet at one particular frequency, 1.4 gigahertz in this case, for example. And from this, I can also estimate the breaking frequency, that is the the frequency at which your spectrum has a sharp cut off, and the spectral index, the slope of your distribution. And by this, then we are building a framework that allows us to build, let's say, the bridge between numerical simulation on one side and observation on the other. So I guess I'm probably running out of time, so I will just leave you the summary here for you to read, and I'm open to question now. Thank you.
Thank you so much, Andrea. That was really a fascinating talk. And I now invite the audience to come and ask their questions. While I wait for people to raise their hands using the Zoom raise hand feature, I would like to ask the first question myself. And that regards the tilt of the jets that you showed at some point, where you argued that basically it's mostly driven by magnetic effects.
Yes.
And I appreciate that point. I think, you know, that makes a lot of sense. But the question I had is that these simulations are fairly idealized in the sense that they don't have an irregular ambient medium. So how is that result affected by heterogeneities in the ambient medium? Could you imagine a situation, you know, of course there are different systems, but could you imagine a situation where you have an AGN jet that runs into a substructured circumgalactic medium?
Yes. Yes.
Where actually the tilt is then driven by other effects, or do the magnetic fields win?
Yeah, the example you are mentioning is the one, for example, for wide angle tail sources. Okay, because in that case, the galaxy is actually falling down in the gravitational well of the cluster, and in its reference frame, okay, it's feeling a wind on one side, and that's an external effect. At this point, we have a medium which is not homogeneous. Well, the medium can also be turbulent by itself, but if we imagine that the wind is coming from one side, then provided the wind has a sufficient momentum, then you can actually deflect the jet as well and creating this structure even without having a magnetic field or a too strong magnetic field. This is one possible situation. The other one with turbulent, as far as I know, didn't prove to be so much successful in bending the jet. So you need a very strong agent in order to bend the jet. So whether this agent can be internal, that is magnetic field, or external, the wind, it doesn't really matter. You achieve essentially the deflection, but it has to be strong.
Yeah. Okay, cool, thank you. Mattia, please.
Thanks, Andrea, for this really nice talk. I have a general question. What is your view on moving mesh codes like Arepo, and how do you think they compare with Pluto and more traditional grid codes?
Okay, so this is my personal opinion. There are advantages and disadvantages. A moving grid code will allow you to access a Lagrangian, almost Lagrangian-like formulation. So the numerical dissipation is very much reduced, which is a desirable effect. However, there are complications due to the grid structure generation. Well, dealing with conservation of the solenoidal constraint of magnetic field is a mess, okay, because everything is skewed, so it's hard to conserve that. And then you have issues with boundary conditions. I don't know, it's difficult to say at this point. Probably, I don't know, in the next few years, I would like to see some sort of comparison between a static grid code and a moving grid code to see, but it can also change very much from problem to problem. Honestly, I prefer to go with static grid-like code because just because the grid generation process is simpler. You can also use, you can improve this code by using grid mapping techniques, for example, without having the grid to move. The grid can stay still, but you can still remap the grid under different grid transformation to get the resolution where you want to. The other thing I could tell you is the following. How often do you really need to use adaptive mesh refinement, or let's say a grid that changes dynamically in time? Because in my experience, let's say 80% of the time, it was sufficient for me to have a grid that has enough resolution in one region, and that region remains the same throughout the simulation. Doesn't change. So in other words, I have a final resolution in one region, and that's it. I don't need to change it.
Okay.
Most of the time. Of course, it's different if you are tracking features in your simulations. But for example, if you study reconnection, all you need to track is the midplane. So there is no need of maybe moving grid in that example, right? So why bothering?
Okay. And a related question, what do you think is the future direction of the Pluto code? Like, what is your plan? What features?
Okay, so the future is GPU and high order methods.
Okay.
So we are working on it. We already have an alpha version of Pluto GPU, but we are still facing some issues with the MPI, which we don't clearly understand. The direction will be to move to Pluto 5 in the future and having truly fourth order schemes and GPU compatible software.
Thank you.
Okay. While keeping the same physics, of course, as much as possible.
Okay, I apologize if you heard me type. I was in the chat trying to streamline the conversation with the next questions. So the next question goes to Christian Fendt.
Andrea, this was super interesting. I have a question about the jet turbulence. So in the first half of your talk, you stressed the point that turbulence is important for jet propagation, you know.
More for dissipation, really.
For dissipation, yeah. And then in the second half, you mentioned reconnection. And so I'm wondering how much resistivity will change the picture in a sense that you also have a magnetic diffusivity which would smoothen maybe the turbulence. On the other hand, you have reconnection that puts energy into the jet locally and probably enhances your turbulence structure.
Okay, first, well, I will answer this question with a warning, because we are carrying very high resolution of reconnecting region now, and what we are finding out is that resolving the reconnection layer is essential, and to do that, the resolution depends on the Lundquist number. So, just to give you an order of idea, if your Lundquist number, you know, the Lundquist number is essentially this non-dimensional number formed by the Alfvén velocity times the system scale divided by the resistivity. So high Lundquist number means very small resistivity. When you increase the Lundquist number, the amount of cell that you should place in your reconnection layer is approximately, let's say, 3 times for each decade. So if you start, for example, S being the Lundquist number to be 10 to the 4, you need approximately 40 zones in order to achieve convergence in this simulation. Now, if you increase your Lundquist number to 10 to the 5, then you need 120 zones to resolve that, okay? So people are most often not aware of this, and they just put resistivity by hand, or they even do ideal computation, which is completely wrong, okay? So making ideal computation of this stuff, and well, of course you get reconnection in ideal computation, but not because, well, because the code has numerical resistivity. The numerical resistivity will trigger the reconnection process, but the rate at which this reconnection process takes place depends on the resolution, right? Because if you increase the resolution in an ideal code, you are just decreasing your numerical resistivity.
Yeah, clear. Yeah, that's clear. Mm.
Okay, so you should end up to the point where your numerical resolution is large enough so that you are resolving the physical resistivity, while the numerical one is much smaller. And the answer is 40 zones for a Lundquist number of 10 to the 4 in our simulation.
Okay.
We have done both MHD and relativistic MHD, and we approximately get around the same answer. Probably slightly more in the relativistic case, but just by a few cells.
Okay, yeah, thanks.
Kees, next question, please.
Yes, Andrea, very interesting work and talk. Thank you very much. I was wondering your shock acceleration models with the turbulence behind the shock. I have 2 questions there. One is that it seemed as if the material coming into the shock, the upstream material, was already strongly perturbed.
Yeah, okay, I will answer that in a minute, yes.
Okay, and the second question is, from your simulations, would you say that your results confirm the more simple analytic model results, or would you say that you actually need such for different situations, you would need to redo your simulation with different parameters to get the actual right result?
Okay, let me answer the second question, which is the easiest one. The answer is yes. The numerical computation confirmed the analytical expectation. Very good. I have not actually, to be fairly honest with you, I have not covered the whole parameter space. Yeah. So for example, I would have liked to do inclined magnetic field rather than parallel. Okay, I didn't have time to do that, but I know other people have been using similar codes and they achieve essentially what the theory predicts. So the field has to be aligned with the shock direction. Otherwise, if you are perpendicular, you kill down the acceleration process. Okay. that's the first question. So yes, we are reasonably in agreement with theory. Let me answer the first question about the perturbation. No, I am not perturbing the upstream. What you see, okay, I know it's a little bit deceiving, but I can explain very easily what happens here. Now, at the beginning, there is no perturbation at all, okay? But we do inject particle at the shock position.
Mm-hmm.
These particles are then traveling in the upstream, and through their current, they generate the Bell non-resonant instability. Mm. The Bell non-resonant instability is the one which is giving rise to this perturbed pattern. Everything is done automatically. There is no external imposed constraint to generate it. Now, once your turbulent medium becomes, let's say, clumpy, these magnetic clumps will actually come into the shock, being enhanced even more, and then the process continue. At that point, the particles, the Bell instability has already reached the saturation level. So each new particle will just go back and forth, becoming accelerated, because there is nothing you can do more. In fact, in this simulation, it's written in the paper, but before counting the particles that are accelerated, we completely remove those particles that have given rise to the Bell instability. Okay, so it's not externally imposed, it's automatically in the process. It's the result of the non-resonant Bell instability. So the process is first generate the instability brings the clumps, and then those clumps are used to accelerate particles. The only thing I can tell you is that in order to make this thing work in MHD-PIC model, you need a recipe that is where and how to inject the particles at the shocks. Because in PIC code, there is no such a need, because you have a pool, I mean, you have everything is particle. You have both thermal and non-thermal, and they are handled in the same way. But here we have a fluid, which is thermal, and CR, cosmic rays, which are non-thermal. So you need to know, how do I make a CR particle out of the thermal component? So I need to know where should that be injected, at what energy. So if you take Damiano Scaprioli paper, there are recipes to do this. For example, the particles are injected at the shock with an energy which is approximately 10 times the energy of the shock. And that establishes essentially the lower threshold for a particle to be considered suprathermal.
Thank you.
Thank you. Okay, next question is for Brian.
Hi, and a very nice talk. I just wanted maybe to follow on a little bit from the previous question, that in reality, in order to reproduce the theoretical prediction, all you need is scattering. That's the only ingredient that goes into diffusive shock acceleration.
Yes, yes.
So the question would be, what are you doing beyond the theory here? And one concern that I always had of the particle and cell simulation, MHD particle and cell simulation, because we did quite a bit of work on this about a decade ago, was that in order to get the correct result, you must spend a huge computational effort modeling the isotropic part of the distribution. And PIC codes are very, very bad at this. So we moved over to spectral methods quite quickly. And found much more diverse range of results. So moving beyond this very simple picture. I was curious if you consider this at all.
No, we not quite. In the sense that all the only ingredient that come in the simulation are essentially, well, the shock, the Bell instability, and the particle themselves. But once we have a monochromatic spectrum given at the beginning, the whole process is carried out automatically without the need of imposing external constraint or nothing. I don't know if I understood correctly your question, but there is no trick being used in this simulation once it is started, after it is started.
Yeah, I mean, I guess the physically interesting question would be, when do you get something different than the standard diffusive shock acceleration picture? Because, as I said, all you need for the standard result is superthermal particles and scattering.
Yes, what I get different, well, in this simulation were done mainly to confirm the analytical prediction. So probably there is more to be said about the low energy tail of this distribution. For example, I found some disagreement between my computation and those by and Spikoski in 2013. The low energy tail is handled quite differently. I have a wider low energy spectrum. Okay, I mean, I'm talking about this part of the spectrum here. Okay, the one that gets sent before the power law. So this is done differently. Now that can have a variety of reasons. Numerically speaking, can be done, I mean, can be due to the way you handle the particle pusher, or the way you deposit and you exchange momentum between density and particle. And also, okay, so there is one ingredient here also that I didn't mention, which is the shock recognition pattern. See, while in a PIC code, like you said, this is handled by the model itself. There is no need to recognize a shock. In MHD-PIC hybrid approach, you need to identify the shock, because this is the place where you want to inject particle. So you're assuming that the suprathermal particle production is taking place, okay, with a recipe. It's not natural. It's not implied by the model. And in order to do that, you need to address the shock position correctly. And that's not easy to do, okay? So we have actually derived a fairly better method than in Bai and Spikoski, although it becomes quite difficult to be extended when you have multiple shocks from crossing. So we don't, I mean, the distribution that you see here is only made up of the cumulative effect of all particles. We are not evolving any distribution function, just to be clear, okay? So we have I mean, millions of particles here, each one following an equation of motion. And all we do at the end is taking the, doing statistic on this huge number of particles. Did I answer your question more or less?
Yeah, I mean, I think I understand.
Okay, so yeah, you are free to write to me, because I think there are more issues to be discussed here, but the story becomes quite long.
Okay. Thank you, Andrea.
Yeah.
Thank you. I currently see no more questions up, and I think no more hands up, and I think we're also approaching the end of our time. But this is actually a great lead into what I wanted to say. If people have more questions, obviously, normally we would have loved to invite you in person, and you would have had a chance to speak with a lot of people individually. Now, if people have further questions, by all means, please either write Andrea directly or write me, and I will pass on your message. So that's the first thing I'd like to say. The other one is to announce next week's colloquium, for which I will briefly steal the screen sharing from you, Andrea.
Yes, sorry.
No, that's all right. Yes, so this is the announcement for next week. Next week we have Nate Bastian from Liverpool John Moores University speaking about very low energy processes, namely the puzzle of multiple populations in globular clusters. And with that, we reached the end of the colloquium for this week. I would like us all to please unmute the microphone again and thank Andrea with a warm applause for a fascinating talk. Thank you again.